Okay, there's a high chance that it's gonna take 2 hours of me monologuing about how awesome chip making can be. And I hope you're interested. This is going to be a lot of new things that potentially can go into your final exam. It will not, well, the things we cover today it will not matter about your lab too much, your project. Well, definitely good to know. Basically, is that there are things that are done in the hardware for you. Wait, what was the video that I sent last term about Intel? Or from Intel? I kind of forgot. Yeah, I forgot what I did. So what is that video? Oh, the CPU architecture. Yeah, something along that line. Basically, today I'm gonna start to talk about, let's say I have a program, right? And I want to run it. I now know the ISA. So I know the things eventually convert to a binary, right? How do I run it? Right? So this is basically the entry into my world. So let's go into that. Before we go into that, let's do a quick review from last week, last Thursday, right? It's about how we can talk to a computer. Computer cannot really understand anything we command them to do except for 0 and 1s, right? Otherwise, the rest are gibberish. So the idea is, let's represent our language into a sequence of 0 and 1s. I can invent my own language. Let's say if I see 1111 followed by a bunch of 0, it means that 1111 is an add instruction. Everything that comes afterward is, what do I add it with and where do I put the results back to? And I can invent whatever language I want to use, right? And that's called the ISA. Sometimes people might refer to this as the assembly language. That can be ARM assembly, x86 assembly. And at the end of the day, also, the second thing is your command are going to be in binary. Your data is going to be in binary. So we use this as an interface between your assembly codes and a computer, right? And we develop some insights into what are the differences between ISA and the architecture or the microarchitecture. So ISA basically define an interface, these are the list of commands that the hardware is supposed to implement. So that the computer, when it runs, the programmer says these commands, it knows what to do. The microarchitecture is the actual hardware that allows the computer circuits to work exactly based on the command given by the ISA. So a microprocessor or a processor is ISA plus microarchitecture, basically the language and the circuits. And there are multiple elements of the ISA, like memory organization, address space. We went through some exercise. Well, okay, let's say we have different addressability. How do you add 32-bit number with byte addressability, or add to 8-bit number, basically 1 byte in a 32-bit addressability? How to support virtual memory. Because it's little Indian, we talk about register, which is a really fast temporary memory, right? Which can vary in size depending on the ISA. The benefits, they are fast, but it requires some area. We are talking about operation and opcode. I'm not gonna go through that recap again because it's probably the third time you see it since the system skill class. So let's go into the new material, right? The first thing I want to tell you is, let's talk about an architecture where everything is done in a cycle. Let's say I want to do an add, take 1 cycle. I want to do a multiply, take 1 cycle. I want to go into DRAM and get my data, also 1 cycle. This is the simplest form of a computer. The ISA, you can think of this as whatever is visible to the programmer, right? That's your interface. I put in assembly code, the ISA tell you these are controllable. Everything that can be controlled by the programmer is in the ISA. This is called architectural state. So architectural states is things that programmer can see. Sometimes programmer can modify. Anything that is seen by the programmer is called architectural state. So things like the name of the register in Intel x86, these are the EAX, right? ECX, and those things. You can write a code to use it, right? So this is visible to the programmer. As a programmer, you can modify this, you can use it. Program counter, you can use it as well. These are visible to the programmer. The memory, right? You can use it by using pointer, right? It stores the location that the index is indexed by an address. So the programmer can directly see and handle these values. But what else, right? In the computer, there are also things that are not visible to the programmer, right? This is called microarchitectural states. No way for the programmer to see this. What are the examples of that? Can someone give me an example of things that programmer cannot modify? At least cannot directly modify. Things that we covered in the last assignment of system skill. What did we do in the last assignment of system skill? The page table, interestingly, can depends on the ISA. It can be managed somewhat by the programmer, by basically the OS. But that's one thing that the last lab of your assignment in how the cache is managed, right? The cache is not accessible. You can tell how big it is, but you have no way to control that manually. It's done all in hardware, right? So these are some examples. You can't control the value of what goes into the cache block. This is hardware managed. You can tell, let's say you do pipelining, which is going to come up next. Like next lecture, we cover what we call pipelining. Basically, how can we make programs even faster when we run? You cannot really control this intermediate value because everything is done in hardware. Why do we need to do this all in hardware? Because it makes your life easier. It makes your life a lot easier. You don't have to manage the cache manually, right? But it will be basically fast. You can go to get your data really fast anyway. So now that we have the ISA, we have a method to actually command our computer, right? What are the hardware? So how do we connect all the circuits together? How do we actually figure out, oh, okay, I see 11111000. It's an add instruction, right? So think of it this way. We just develop what we call the architectural state. So what is an architectural state? Can someone tell me? Well, basically, we defined it a few slides back, but what is an architectural state? It's everything the programmer can see, right? It's the state of the machine that the programmer can measure, see, access. Process one instruction. I am going to run into the second architecture state. Basically, this is the way computer run. I have a state. I execute one instruction. I move from state 1 to state 2. I run one more instruction. I move from state 2 to state 3. Your entire program is to change from architectural state 1 into architectural state n, where n is billions of instructions later, right? After billions and billions of instructions later, once you have the sys call that say, I stop this program finish, here's the return value. That's it. You can see the result of your program, right? So basically, this is how you process the instruction. So in a single cycle architecture, what do we need to do? First, look at the instruction. Second, check what's the original state. Third, from the original state, how do we move into the next state based on my instruction? Everyone with me so far? Basically, I have one line of assembly that tells me to do something. I have architectural state. That one line would modify that architectural state into the second architectural state, basically the next state. So what do we expect, right? ISA specify, basically the ISA that we learned from last lecture would specify how a architectural state 2 should look like, given the instruction, given the original state. So what's missing here? From the programmer point of view, right, to get from AS1 to AS2 is one step, one instruction, one step, right? So what's missing is the hardware cannot hide anything in the middle. We built the hardware to kind of jump from instruction to instruction, to the next instruction, to the next instruction. As the hardware designer, we never really tell them what's going on in the middle. Why is that the case? Again, to make your life simple. Don't worry about it. It's correct. Here's the value. Good luck. Hopefully your program has no bug, and hopefully your program run and execute correctly. Yay. Right? So the microarchitecture, the hardware basically implements how we get there. Basically, this process, the process of moving from architectural state 1 to architectural state 2. There can be any number of immediate steps in the middle, right? Single cycle architecture, there's only one big step. Multi-cycle architecture can require multiple steps that are smaller. There are many design choices. You can buy a really wimpy processor that would work if you want to overlay, say, your air conditioner, your refrigerator, your microwave, right? Those are simple. You can get a full-blown supercomputer. It depends on how much, I guess. What is the difference between a chip on your mobile phone versus a chip for a supercomputer? Can someone tell me what would be the difference? So the mobile phone chip, it doesn't have to be that fast, right? But these days they're actually really fast. It might cost less, right? It might not have to support the concurrent execution in the same way of a server grade processor, because in a server you probably run like thousands and thousands of things at once. On your mobile phone, what is the only thing that's showing up on your screen? There's only one app, right? At the end of the day, you have only one foreground application. Everything else is background, right? So design choices matter, right? You can have AS1 moving to AS2 in one clock cycle. I'm gonna make everything easy to design. It can be from AS1, temp 1, temp 2, temp 3 without telling the programmer. I'm not gonna tell you anything, but there's a lot of intermediate steps in the middle into AS2. For example, right, your modern day Intel processor, to move from AS1 to AS2, anyone want to take a guess of like a rough number of steps to go from AS1 to AS2? On average, or like rough number, basically a ballpark number. So actually, to be honest, the number 5 is a really, really good guess. There's a lot of ARM processor that used for embedded system that use a 5-stage pipeline. So that means you go five stage, temp 1, temp 2, temp 3, temp 4, and temp 5. In an Intel processor for your CPU, this can be like 30 something stages. It's a lot, right? It's a lot. You spend 5 to 6 states just to get your instruction. Another 5 to 6 to figure out, okay, what instruction is doing. And then maybe 10 more instructions to do the multiply, right? And then a few more to handle this data access. So these middle steps can be as many as required. It's a design choices, right? What are the trade-offs? The trade-off is, first of all, complexity. So if you have 30 intermediate steps, is it more likely to be buggy compared to, let's say, 2 steps? It is, right? Because you need to figure out, okay, what do I do in these steps? Do I cross over and somehow have a bug that this value disappear. Yeah, it can happen. It can actually happen in hardware. Your value can actually disappear because everything is a wire, right? So if you don't put the value on the wires, it's gone. So this thing can be the hardware bugs. So the complexity is different. The speed is different. At 30 to 30 something stages, when you cut the pipeline, cut the design that frequently, you can clock it really fast. That's why you can have the 3 gigahertz processor, 4 gigahertz processor, and you can maybe turbo boost it to 5 gigahertz, right? Because you have a much smaller steps. Think of it this way. If I have to walk, right? Think of if I have a wide step, like let's say I only have 5 steps, it means I have to walk really, really wide. Each step is really wide. But each step, if I have to go wide, right, it means it would take more time for me to walk per step. The same thing goes with clock cycle, right? So if I have only say 5 steps from AS1 to AS2, the clock cycle would be longer because I would need to take time to walk each step. But let's say I want to now slice it to a really, really tiny step. It means that each step I can go a lot quicker, right? Like this, rather than going like this at a time, right? Same thing here, same concept. Why is it the same concept? Each step cover a distance. What is an electron? How does electron move, actually? So what tell you the speed that electron can move from one location to another? Voltage, right? Basically, electron is a physical thing. When you move from one location to another, it takes time to travel. When you slice things into the smaller step, the distance is smaller. As simple as that. The distance is smaller, so you can clock it faster. So as I said, we cover some background like wires already, register, mux, and demux. So we're gonna use it today. I'm gonna draw some diagram that based on mux and demux and register. These are some of the things that I really, really want to make sure that if you have questions, let me know because these are all new. I'm sure these are all new because there's no digital design classes for a student for CS, but these are the basic elements. And we covered that on the first lecture. If you forgot and I draw something that you don't recognize, let me know. All right, because I'm gonna start drawing a lot of things. Combinational logic and sequential logic. This is a little bit new. Combinational logic is basically AND or XOR. Basically, when you put those together, we call it combinational logic. What does it mean? Let's say I have the AND gate. And this is OR, right? And OR, right? And then I guess not. What we can assume is when I have the input X, Y, C, A, and then out, right? What I can assume with combinational logic, it means that when I have all the input, I can assume that the output is that function right away. It's a combination of logic that put together produce an output. This should be done within a cycle. When I have the input ready, I can compute what is my output within a single cycle. Sequential logic kind of means that if I want to say put value data in to my register, right? Data out, and I put a clock here. When I clock, data in will be stored based on the register number. Basically, let's say register number is 1, and let's assume 1 represents EAX. The next clock cycle, EAX would take in data in. whatever value is at data in, it would be stored in the register, and we call this sequential logic. It kind of process from one clock cycle to another. This is how we can manage to move from one state to another over time, right? Over time. Any questions so far? Any questions so far? Or I guess the last thing is clock, right? Clock should be factored in. Is it a refresh? That's a totally different thing. We'll talk about refresh when we talk about DRAM. That's totally different. This is more like how we can store things, right? Let's say I have a memory and I want to put data in my memory. We use sequential logic. Sequential logic would kind of like a way for you to store intermediate steps. And combinational logic are basically compute elements that within a cycle you should see the output. The last thing I want to make sure you are aware is these two have to do with each other. Whenever I say critical path of your design is, let's say you have a big design, right? Logic. And input is here, output is here. Critical path is the slowest path from the input to the output. Why is that important? It tells me within one cycle, I need to make sure the electron goes from the input, propagate all the way to the output. So that's my critical path. That's the slowest path the electron can go. Why is that important for the clock cycle? Oh yeah, sure. So there's a question on, can I reiterate the sequential logic? Sequential logic basically means that it's a logic that I use to store any temp variable, right? So let's assume that this is a programming world, right? You can kind of let's put that hat. Now we are programming something. How many times you use a temp variable to store internal like computation? You use it all the time, like temp1 equal x, and then you use temp1 later, right? Think of it as a sequential logic. We use that to store intermediate steps, right? So the question is data in every predetermined cycle, so it auto updates whenever data in according to clock. Yes, whenever. So usually there's another input that say enable. The enable means that when this is 1, I'm going to store new things into it. If this is 0, I'm going to ignore what was in data in. So this is how you can program and store temporarily variable. If I have data input into my register, I want to store it at this cycle. What do I need to do? So let's say I want to store number 20, right? So let me change the color to make it clear. So let's say I want to store 20. So right now 20 is in data in. I really want to store this value so that in the next cycle, the register has the value 20. What do I do? So let's say I want to store 20 in EAX, and let's say EAX is number 1 in the register ID. I would do this. I would say I'll put a number 1 in here to make sure it's EAX. I'll put 20 in the data in to make sure the data input is 20. The last step is I want to make sure this is enabled by signal that to be a number 1. Bit 1 means that I'm going to enable this, put 20 into my register at EAX. In the next cycle, number 20 will be stored here. Any cycle onward, whenever you want to read from EAX, it will now become 20. So that's sequential logic. The reason why they name it sequential logic is it's a sequence of time, right? Once you do this, the next clock cycle, your value will propagate. Is it more clear? So any questions that follow from this, or should I explain it again? Yeah, so clock will go between 0 and 1, 0 and 1, 0 and 1, 0 and 1, basically. Every time it alternates, that's one clock cycle. So if you go from 0 and 1 and back to 0, that's one clock cycle. So yes, so there's another question that says it will store 20 in the next cycle, right? Yes. In the next cycle, 20 will be moved into the register. It will be moved to the register in the next cycle. And this is how you can store things, right? Let's say you have all this component, you can build a computer, right? Basically, you can build for what can you build? You can build register files, right? You have a register. To make x86 work, what do you need? Register. You need a memory, right? DRAM, you can buy that. You need the adder, multiplier. Adder and multiplier, these are combinational logic. So with this, you can build anything now. With this, you can build anything. Critical path will tell you how fast is your computer. How fast is the computer? Because it tells you how long does it take for me to move this electron all the way to the output. So that's why we call it critical path. Path in English means something, I don't even know how to define path in English, but you know what it means. Critical path means that that's the most important part in the processor, because you move from the electron from the beginning to the end, and that's the furthest distance the electron has to cover. So that's a critical path. So let's talk about single cycle processor. Single cycle processor basically means that I'm gonna move from architectural state 1 through some combinational logic into architectural state 2 in one cycle. So basically every single instruction defined under the ISA take one cycle. So let's assume that. Let's assume that first. Once you are in AS2, right, you store what happened. You store this architectural state in the sequential logic, as I said, right? It's a storage element. You store that, rinse and repeat, right? So this is next instruction. So this is our single cycle processor. This is the simplest form of a processor. Any questions so far? Basically, with some combinational logic like add, multiply, we change AS1 to AS2. Once we are at AS2, we make sure the result is stored in a register or in some address in the main memory. That's a sequential logic. Repeat, 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 repeat until we finish the whole program. So this is our simple processor called single cycle processor. In this case, let me ask you, what would determine the critical path of our combinational logic? So let's say I have an add instruction that takes in one cycle. I mean, not one cycle. Everything still take one cycle. Take 1 nanosecond. A multiply take 10 nanosecond. Let's say I only support two things. I can add, I can multiply. And my single cycle processor, I said everything has to be done in one cycle. So how fast can my processor be? So what would be the clock speed of this particular processor? Let's assume I can only do an add and multiply. What's the maximum clock speed? So 1 nanosecond is 1 gigahertz. 10 nanosecond is 100 megahertz. Can I clock it at 100 megahertz or can I clock it at 1 gigahertz? It's actually 100 megahertz, right? Because that's the fastest I can go. If I go any faster than 100 megahertz, it means that I cannot do multiply. If I want to do multiply and I clock it faster than 100 megahertz, the electron will not arrive at the output. Because I need to wait 10 nanoseconds, and anything faster than 100 megahertz take lower than 10 nanoseconds. It means that I will never have the result of my multiply, right? So let me ask this. In this case, if I want a single cycle processor, what would be the factor that determine my clock cycle? It'll be the slowest instruction, right? In your ISA. Whatever is that slowest instruction, that becomes your clock cycle, right? So let's say a multiply takes 10 nanoseconds, a load takes 50 nanoseconds. It means that now my clock cycle is 20 megahertz. Yay, even slower, right? So it's simple, but it's bad in terms of performance. But we'll go with simple first for now. All right, with me so far. So here is this. The slowest instruction across every instruction in my ISA will determine the clock cycle for a single cycle processor. And we'll fix it in the future. And let's say, what if I need to access the hard drive? Right? That's probably the worst. That would take microsecond, right? So your clock becomes less than megahertz, right? So you probably do not want a 1 kilohertz processor. That's too slow, right? But let's study how we can build one for now. We can build one for now. A side question is how we measure performance. Well, we'll table that question so far, but ponder about how do we measure performance in a bit? Because everything here is we want to design a chip that are fast, right? So what happened in one cycle, right? The first thing you have to do is, well, basically we process one instruction. That's it, right? In one cycle, we process one instruction. So recall from lecture 2 and 1. Is it lecture 1 or 2? That instruction in memory. Basically, recall from system skill, your instruction is in the main memory. Your program is in the main memory. So the step is this. How do I get to, what's the first thing I have to do? From sys skill class. So what's the first step that I have to do? I would have to fetch the instruction from the ISA. Not from the ISA, from where? Where's my instruction? Memory, correct, right? So you need to go to the memory. So first thing you have to do, go to the memory to figure out, okay, what's the instruction? What's that line of assembly? Once you have that, what do you do next? Let's say you're just human, right? You are human that want to go figure out what is this instruction and perform the task. Now that you have this jumbo binary ones and zero, what is the next thing to do to figure out what you're supposed to do? You decode, right? What we call is decode an instruction. So fetch is go to the current line of your assembly program. To get the instruction, decode basically means that based on that binary, ones and zero, based on the ones and zeros in the instruction, figure out what are you supposed to do. Figure out what is that instruction. So this decode step, remember our assignment 3 part 2 of system skill, the disassembler? This is the decode thing. You figure out, okay, I see this binary. This is what it's supposed to do. The next step, once you know what you're supposed to do, evaluate any address that you have to go look up, right? If you need to go to the memory, you go to the memory, and then fetch the operand. What is an operand? Yeah, any variable, any data that associate with your instruction, right? If you want to do an add, then your operand would be what are the numbers you are supposed to add with, right? Parameters that are being passed in. So you go get that and you run it, execute, right? Perform that instruction. So once you perform the instruction, what is the last thing you have to do? You store it back. you have the results, so you store the results back, and that's it. That's one instruction. These are the common steps, and that is it. Let me actually write it. That's it. That's all. That's all per instruction, right? So once you break it down this way, it's simple. Every single instruction in the ISA follow this step. Go to the memory, figure out what is that binary value for the instruction, decode what are we supposed to do, evaluate the instruction, execute, and then store the results back. Once you are done, you're at AS2, architectural state 2. Rinse and repeat until you finish your program. And note that not all instruction doesn't require all the steps. For example, a load instruction doesn't execute much, right? Or an add instruction might not have to go to the memory to get your data, right? But these are general steps. Any questions so far? But hopefully it's more clear on what are you supposed to do in terms of step by step. So with this, right, I want to tell two more terminology, two additional terminology before we can proceed on, because these are the two things that if you check with the textbook, you see some of these get referred to. Data path and control logic. As the name suggests, what's the data path? So break it down that word into data and path. What are they supposed to mean? It's something that has to do with data, right? It's something that has to do with how you process your data. A control logic typically means that it's a signal that you use to control your computer. So when you process an instruction from data, the original data D1 into the next piece of data D1 prime, D1 prime is a math function basically. D1 coming in, function, which can be just add, right? And then you get D1 prime. You add something from the original data, you get the new data. This is done to what we call a functional unit. Basically, it performs the operations on the operand. Instruction would tell what is that operation. And when you process this, it consists of two components. The first is data path. Think of this as the hardware that deal with the function to transform D1 to D1 prime. Anything that are related to that process. Things like logic gates, wires, mux, and the storage element like register. These are data path. Control path is basically the hardware signal that control do this add, don't enable the multiply, for example. Because in your computer, you're going to have a logic specifically for an add, another separate logic for a multiply, another separate logic for an AND, an OR, an XOR, right? The control logic would make sure that if you have to do an add, you enable an add. If you want to do a multiply, it only enable the multiply and don't do everything else. So that's the control logic. Any questions about these two terminology? Before I go into the question on the chat that say, can I evaluate the address? So to answer about how to evaluate the address, remember our instruction? It comes with, say, opcode, right? Operand. Remember addressing mode, right? Where you can do like load 0, R1, where R1 becomes an, if I do this, right, this is an address. So how do I get the address here? For example, how do I get an address here? So I want to, is a pointer, right? Who stored the address? It's in R1, right? You go to R1 to get the address. So this is one example, right? You go to R1 to get the address. Once you have the address, here's your DRAM. This is literally what happened once you have the address. You put in the address saying, I want this address. The data output from DRAM would give you, eventually, would give you the value of that address. There are more things involved here, but in a really super high level, you give them the address, you're going to get the data of that address. So these can be coming from, let's say you have a register file, right? You put in this particular example, you put in R1 for the register select. You select R1, you want to get the value of R1. Enable is 0 because you don't want to enable anything. You're just reading, you're not writing. Right? And then you connect this data output, which is the value of R1, you connect to the address that go into DRAM. So this way, basically, you make a connection between the register files to DRAM, right? And you can imagine there can be many other types of input that go into the address signal that come from the, for example, immediate, or come from the result of adding R1 plus 20, for example, right? So R1 plus 20 would be something like this. You have the data out, right? And then you add immediate from your instruction before that goes into the address. So now I have multiple inputs into the address signal of DRAM. What do I need to select? I will have a mux, right? Remember our mux? Mux have multiple inputs. You select which one go in as the output. So one thing I can do here is I have, say, 3 inputs, right? Oops. Sorry, I'm not supposed to use highlighter here. Too hard to see. This is a mux. 0, 1, 2. Address. And the select line, right? The select, if I select 0, it means that I'll take the address directly from the register file. If I select 1, it means that I'm going to take register files plus some number. If I select 2, it will basically directly come from the immediate. Let's say you do load 0, 21, right? 21 will go directly, in this case, as an address. So hopefully this is more clear, or do I just mess things up and it's more confusing? Any question from this? Basically, you have multiple wires coming in as an address. You would select which one are you going to use as the final. address. The select is the control logic. Yeah, so the output of the mux will be only one thing. You cannot select 5 addresses, right? There are more little details going forward, but for now, with our simple processor, let's go with this. Let's go with this. All right, are we good? Ish. I know this all are new to you, so if it's confusing, please let me know. If it's confusing and you have no idea how you're supposed to frame your question, feel free to let me know in in Discord or email, because I'm sure this is new and confusing to you. Right? So I'm trying to make sure I break it down as much as possible. That's a great question. Can I have multiple address going to DRAM at the same time? With modern processor, there are a lot of hardware tricks that you can do to handle that. So we're not going to talk about it in this class. That is totally possible. That's totally what we've been doing in hardware, but we're not going to cover it for the class, of course. Otherwise, we need an entire semester for that. All right. Think of it this way. Simple processor. Let's stick with this for now. Remember, in the real chip, we can do this. So, what do you need in a processor? So let's actually have a blank slide, right? Let's say I want to build a computer. What do I need? Type something. I'm sure whatever you type first will be correct. And you're gonna have more limited choice. You need Yes, you need transistor for sure, of course, and you also need money. I can't argue with that. Okay, let's say I have money. How do I use my money? Silicon transistor motherboard. Okay, we have motherboard. You have the CPU that plugged in on a motherboard, right? What else are on the motherboard? Yes, capacitor. What consists of capacitor? Okay, GPU is here. Uh, do you need a GPU sometime? Yes, sometime no, depending on how crazy you are with the video processing. You need DRAM, right? And basically you need a lot of controller. So that's where the motherboard comes in. It helped control a lot of things, right? It helped control a lot of things, especially like your input from, say, your hard drive, right? In this lecture, we'll focus on this. All right, we'll focus on this, the CPU, the CPU. There's actually content for the DRAM part, but we'll focus on the CPU first. I mean, okay. So let's zoom in into the CPU, right? Remember our step to process the instruction. Remember our step to process an instruction. What are the 4 or 5 steps or 6 steps that we have right now? Fetch, decode. Okay, awesome. So basically you have DRAM, right? And let's say you have program right here. Sometimes we call this .text. You have seen it on a simulator, right? That is your data. Sometimes we call this .data in the simulator as well from last week, right? So you go get your program, fetch. What's the next step? Decode, right? A decode will have a unit called the decoder. We will not discuss how this is implemented, but it worked the same thing. It worked the same way as last semester system skill disassembler. If you look at the hardware description language, work almost the same way. If you like writing code in a giant if-else statement, this is your friend. It's a huge giant if-else and switch case statement. Decoder works like that, right? So what else? What are the inside the CPU? So what is EAX, ECX, and all those things? Register, right? And yes, I agree that giant if else is not a good design. In this case, use pattern matching. If you're in the parallel programming and functional programming, we will cover pattern matching. It is a basically giant switch case, and the decoder works like that. You do pattern matching. You have register, right? Register file. Why do we call it register file? It's a bunch of register. EAX, ECX, EDX, EBX, R9, R10, R11 to R16, right? And you then also have the interface with the data, right? You can read from DRAM, you can write to DRAM. Inside the register file, there'll be a program counter. Basically, this point to the line that you're reading, right? Are you with me so far? Basically, that's the elements of what goes in your processor. These are the basic elements, and we'll stick to that. Any questions so far? Because I'm gonna start drawing things in a blank canvas again. So remember, we need a way to read the program, the assembly line. We need a way to decode them. We need to handle the register files. Then we have to have a way to read and write things to DRAM. And then we have to have a way to proceed to the next line, right? Because if we cannot proceed to the next line, we're screwed. Your program will not proceed. That's all. That's all we need in the processor for now. Okay. So if you look at PDF, there's a lot of blank slide, right? A lot of blank slide. But let's put everything together. I'm gonna kind of break it down into steps. So this is a fetch step, decode step, execute step. This is basically whatever you have to do with memory. See 5 steps, right, back. The other thing that's supposed to be in your processor is what we call the ALU. I forgot. This is the most important thing, and I don't know why I forgot about it. Anyone know what is the ALU? It's arithmetic and logic unit. This is your brain. This is your computer's brain. What I just draw earlier is I draw storage elements without the brain. Now you have the brain. All right. So the ALU handle things like add, multiply, any logic operation. All right. So I have the ALU. Let me put that in the execute step, because once I know what instruction am I working on, I know exactly how to proceed with it. Right. ALU is here. Let's put DRAM here. And I'll specifically put program in here so that this is basically high level. In the real sense, we have virtual memory to figure out where things are. And this is where your data is. Right? So you fetch. How do you fetch? How do you figure out which line of your code you're accessing? What do you use? Program counter. So let me actually draw a specific program counter in the fetch state, right? Just to make it easy to draw, because things would be more complicated. So PC would read this part of DRAM that say, hey, this is the instruction that you're supposed to run, right? The data comes to the decoder. So once you have the binary of your instruction, you feed it into the decoder. Decoder would do what? It decode, right? And it would say, first of all, it will tell you what are you supposed to do with the ALU? Control. It first of all, control the ALU, right? So actually, let me use a different color for the control path. So let me use a red arrow sign to specify the control. So this is basically tell, is this an add? Is this a multiply? Is it an or this is has nothing to do with you? We just want to get the memory part, the data from the main memory, right? What else? What are the type of thing that instruction can do? It can go get something from the register file, right? I will just put in RF because I don't have the room. This is register. So if I have an add, let's say I have an add 0, R1, R2. Basically, I want to add R1 and R2 together into R0, right? What does the decoder do to the register file? It need to get R1 and it need to get R2, right? So what else do I have to do? Select R1, select R2. I will say, hey, I want R1 and I want R2. In this case, the register file has 2 ports, 2 input ports to read. Okay, I want R1 and I want R2. Right? With me so far, let's say I want to do just an add, right? So this control be add. Okay, what's next? Now I figure out the add, I gather the operand, right? So this is basically where I gather the operand. Now I have the operand, I know the instruction I have to do. Who is the one that's performed this instruction? The ALU, right? So I'm gonna forward R1 and R2 into the ALU. Because I want to do an add, I know I have R1, I have R2. I feed them in. The result would be R1 plus R2, right? Okay, with me so far, basically by now we execute the code, we do an add, we have the results. What is the next step? What is the last step here? I have the results, I have to put it back. Yes, I have to store, right? I have to store back into which register? R0, right? So in this case, again, the decoder sneak in that say, I'm gonna select, oops, sorry, wrong color, my bad. Sneak, still wrong color. Sorry, fat finger, sorry guys. Select R0 for a write, right? I say I want to write into R0. Then from the data part point of view, I'm gonna forward this in as an input. Now I have the result. I'm gonna select R0. So what will happen to R0 in the next cycle? So in this case, it will be written into, right? So in the next cycle, R0 would take in R1 plus R2, right? It's as simple as this. So processor design, if it's single cycle, it actually can be really simple. R0 would change. It would take the value of R1 plus R2. Then what's next? How do I go to the next instruction? Increase the PC, right? Let me call this next PC. Depending on the size of your instruction, this next PC can be like PC plus 4, PC plus 8, PC plus 16, right? It go to the next line. And then there'll be some logic from the decoder with a select next PC. Why do you have to select next PC? Sometimes I have branch in the code, I jump, right? So your next PC can be from the memory. So that's it. This is our functional processor that can do one add, right? Any questions so far? Any questions so far? So from the design point of view, this is functional. From the implementation point of view, which we will not cover because we need digital design. Basically, you have to implement how the decoder would look, how the ALU would look, how the register files would look. For the purpose of you going to actually in a job market and work, this is probably the most you have to know. Unless you want to build a processor, right? So this is basically right about like where we kind of wrap things up into basic processing, super basic processor design. So let's do a simple add, right? Here is add R0, R1, and R2. And let's start with our toy ISA. So now I'll have a real toy ISA. It's a really, really simple ISA. You have 8 register files. So 8 register files, how many bits do I need to represent all 8? I need 8 bits, right? By the way, I think someone is delivering something, so let me get the door. I'll be right back. Give me 1 minute, all right? All right. So if we have 8 register files, I need 3 bits. I can represent 8 number from 0, 0, 0 to 1, 1, 1, right? 2 to the 3 is 8. With this, I also have, let's assume we have a 3 address machine. So I need source 1, source 2, and destination. What else do we need? The opcode bits, immediate bits, right? And right now we are defining our own toy ISA. Let's make it really simple. And here's the table. If I have a compute, which is, let's say, add R0, R1, and R2, I can just say whatever opcode for the add, 0, 0, 0 for source 1, 0, 0, 1 for R1, and 0, 1, 0 here for R2. Again, toy ISA, right? In the real ISA, it's going to look similar, but more complex. It would support many, many other instructions. So let's say the opcode for an add is this pattern, 0, 0, 0, 0, 0, 1, 1. Let's say opcode for a load immediate is 1, 1, 1, 1. Branch can be 0, 0, 0, 0, 1, right? I want to do add R0, R0, R1, and R2. What do I write here? So this is destination, source 1, source 2. What would be the binary for my instruction? So what would be what's the opcode for an add? I said add is 0, 0, 0, 0, 5, 0, and then 2 1s, right? So binary for my add instruction is starting with this, right? So that's the opcode part. How do I put source 1? What is R1? What is number 1 in binary? 0, 0, 1. Right? What is source 2? 0, 1, 0. And what is destination? 0, 0, 0, right? So if the decoder see this, if the decoder see this particular bit pattern, what are you gonna get is at R0, R1, R2. That's all, right? With me so far? Basically, if you see this bit pattern pass through the decoder, you know exactly this add R0, R1, and R2. So this is our toy example, kind of like a nicer version that I draw. This is your DRAM. It takes the address, it gives you the data, and the data can be your instruction right here or the data out right here, right? This is your program counter. Sometimes, as I said, we call instruction pointer or IR. So what do? Fetch. So we put in the address, right, into DRAM. That's fetch. We get that instruction, which is, right, add R1, R0 into destination R1, R2 into destination R0. So you're gonna get that back. That's a fetch. That's it. Any questions about the fetch before we go to decode? So the fetch has to do with this part of your diagram. You look at the PC, you get the value, you got instruction back. So let's do a decode, right? So decode comes in, your data, your instruction value is again 0, 0, 0, 0, 1, 0, 1, 0. Sorry, I forgot. 0, 0, 1, 0, 1, 0, and 0, 0, 0. It goes into this. What does the decoder do? First of all, this is add to register, right? Add to register together. So what should be the input of this select line? What should the decoder do with the select line here? And I'll put in 0 and 1 here. What should it pick from? Should it pick from the register files or should it pick from the immediate from my instruction? So do I select 0 or select 1? It should pick whatever come from a register, right? Which is these operand. So in that case, I'm gonna put the value here to be 1 because that's a mux. Basically, when you see this rectangle, like this slight rectangle, this is our mux. This always represent a mux. This shape is always a mux. So if you put select to be 1, it would forward the whatever is connected to the value 1 here as an output. And in this case, we want exactly that, right? We want whatever comes from the register files into our ALU, which is this. With me so far? So that's the first select. All right. What should I select from the register? Yes, the register indicated as an operand. So in this case, R1 and R2, right? And eventually it's also want to select R0 as well because you want to write the result back in. So you read from R1 and R2, forward that to the ALU, right? The decoder would select 2 more things. It would select 2 more things, but we'll go to that a little bit later. Right? In the fetch operand, as I said, this is R1 and R2 will be select here. And this select line will put in value 1, right? Because it need to forward the data from here into here. Then you execute, which is basically now over here, you have R1 and R2 as an input, right? R1 and R2 as an input. Your data would become R1 plus R2. So that's execute. And what's the last thing we have to do once we have the result? store them, right? So R1 plus R2 comes in here. Select 0, 1, 2. Which one are we selecting here? Are we putting the value 0, 1, or 2? So from 0, it can be something like jump to this line. From 2 come from memory. If you select 2 is a load instruction, you get some data from the main memory. But it's an add instruction. You want the data from your ALU, right? So you're gonna select 1. Yep, 1, right? Because you want the data from the ALU to be forwarded into the register file. So this one you select R0 so that you can write R0 back with R1 plus R2. We are almost done. We are almost done. This is the only last thing left. Once we store the result, what is the next thing we have to do? Next PC, right? So what should the decoder select for the next PC? Let's assume this is 0, 1, 2, and 3. We are not jumping, right? We are not jumping to a register value. We are not jumping to a line in your code. We are not jumping to any result from your ALU. So which one are we selecting? Basically next line, right? Next line is PC plus 4. So select would put the value 0 here to get PC plus 4. Right? And that's it. To process one instruction in one cycle, you need to do everything I just described earlier in one cycle. All right. Oh, why is it 4? So this is for the sake of, like, let's say one instruction is 4 bytes. It can be any number. Basically, this is PC plus n, where n would point you to the next line of your assembly. In x86, this can be plus 1, 2, 3, and 4, depending on how many bytes you're skipping. In MIPS, for example, in MIPS architecture, it's PC plus 4 because every single instruction is 4 bytes. So the MIPS simulator that you saw earlier from last week is PC plus 4. It's simpler, as I said. So basically, that's the value when you have to proceed to the next line in your code. All right, with me? Okay, so basically that's about the high level idea that I want you to extract out of this. This is single cycle architecture, right? All the control signal that I described earlier are generated in one cycle. You perform this R0 plus R1 into D1, write it back to R0. No, my bad. You perform R1 plus R2 and write it back to R0 in one cycle, right? This is kind of bad, as we said, because this would be as slow as the slowest instruction, which is something like you go to the I/O, right? You have to wait from a data from your hard drive or something like that. So that can be slow. The next step is I can have multiple cycle processor where the control signal is generated on the cycle that I'm on. So let's say I do an add, which can take one cycle. I can generate every signal in one cycle, and that's fine. If I want to do a multiply, and because multiply involves multiple adds, right? You add a bunch of numbers together. This can take, say, 5 cycles, right? So in this case, what can I do is when I see a multiply instruction, the decoder has to time the select signal at the correct cycle. These allow you to decouple the time it takes for you to finish the instruction, such as multiply, load the data from the main memory, store something to the main memory from the decoder telling you these are the signal I want to apply. And we'll go into more detail later. In next lecture when we go to pipelining and basically explain how can we speed up things even further. All right. In the multi-cycle architecture, when you process an instruction, right, you fetch the instruction from the main memory, then you decode, then you get out the operand, same steps, right? Then you move to the next instruction. So let's go back to our toy example, but, okay, so shall we take a quick break here? Because I feel like you're freezing. Everyone is kind of freezing at the moment. Okay. All right, so let's do a 5 minutes break where you can ask questions, pummel me with questions, use the time to process information so far, and I'll shut up. Except for answering questions, all right? So I'm gonna pause the recording and let's do a brief break / Q&A. But let's resume the recording. If you still have questions or marks when you watch the video, let me know. So how do we process an instruction, right? We get it from the main memory. Decode, get all the operand, execute, and write or record the result back, and we move to the next instruction, right? So let's go back to our toy example. And I promise we only have a few, well, not a few, but it's a lot of like figure. So should be roughly, hopefully not as packed as earlier part of the lecture. So let's assume this. If I have a memory instruction that take one cycle, right? A decoding logic that take one cycle. When I access a PC to read or to write one cycle, access a register one cycle, every ALU would take one cycle. This is multi-cycle architecture. Things would take shorter amount of time. So in this particular setup, one cycle is a lot smaller, but you can do a small step at a time. So what would happen if I do an add, right? I want to do R0 plus R1 equals R2. If I want to do this, how long does it take for me to get to read this? With the assumption earlier. Basically everything takes one cycle, so how long does it take to read from the PC? So everything takes one cycle. I would spend one cycle here, right? I'm just going to say +1 here, and we add the tally. How long does it take? If you did everything, yeah, 6 cycles. So +1 here. You then read from the memory. So there's one more here, one more to decode, one more to get the register, one more to do an add, and then one more to write it back here. Quick note, you can do this in parallel as you do this part, because it has nothing to do with each other. You have PC +4 already, so you can do it right away at the same time, right? So when you add all the number together, what's the final number of cycles to do an add? So it's 1 plus 1 plus 1 plus 1 plus 1. That's 6 cycles, right? How about a multiply? We have a magic ALU. Everything takes one cycle, so this would take in total the same amount of cycle as an add, right? 6 cycle. Because everything is the same, basically, except for just change the add to the multiply. How about this? If I say I want to load something, basically I want to load something from this address into R1. One cycle here, one cycle here, one cycle here, right? This go directly into the ALU, which forward to your address. So one cycle here, one cycle here, and then one cycle here. 1, 2, 3, 4, 5, 6. Also 6 cycle. Right? So this is basically magic memory and magic ALU. Everything take one cycle is super magical, right? So let's make it more realistic. With our one magic cycle memory, everything here would take 6 cycles so far, right? This kind of seemed kind of slow, right? First thing first, this kind of slow. So one optimization you can do is in real processor, the XOR, the load, the add, because they are doing different things on the ALU. If you go back over here, ALU has the adder, it has the multiplier, right? So you can actually do that processing at the same time. You can do all this at the same time. So that's one thing you can make it faster. But we'll forget about that. We don't forget about the fact that it can be done in parallel. But we'll not worry about that yet. That's too advanced. But just be aware that when you have add and load and XOR, this can be done in parallel. And your CPU is optimized to do that. Can we also make things faster? Yes, through pipelining, which we will learn on today. The problem is this. If I go back to a data load, right, over here, and now if I tell you that a memory access take 100 cycles, how much time do I need to do this load value? One cycle here, right? I go to get my address for the instruction. How long does it take? Yep, 100, right? And then one cycle here. Nope. Then you go to here, one cycle at the ALU. And I now have the address. How long again? Another 100, right? And then you write it back plus 1, right? So over here, instead of 6 cycles, you take 204, right? Now, do you realize how important is DRAM here in terms of the speed? And this is reality, right? This is the thing that I really want to make sure you are aware. That's why caching is so important, because caching would make that 100 cycle down to 2 to 4. It would move it back to like 2 to 4 cycles. It's a lot faster. So with our magic memory, everything kind of takes the same, but with real memory and real ALU, right? Add basically XOR is the fastest. XOR is the fastest, followed by add, followed by multiply, followed by load. XOR is one logic gate. That's the simplest. Right away, you're done. Add is a bunch of gates together, so it would take a little bit more time. Multiply is a bunch of add. Load means you go to the memory. That's the slowest one, right? So in reality, if you have this different amount of time, if you have a single cycle architecture, which one determine my clock cycle? Let's say these are the only 4 instructions I support. Which one determine my clock cycle? Everything take 1 cycle, so I have to make the clock cycle based on the load instruction. How many cycles? How much time does it take for me to do a load, right? In the multi-cycle architecture, now I can make a clock as fast as my XOR. I can do XOR in one cycle. If I have to do an add, well, maybe 2 or 4 cycles. If I have to do a multiply, it might take 10 cycles. If I have to do a load, 2 or 6, 2 or 4, right? That many number of cycles. But then in this case, for a single cycle, I might have to clock things at 1 kilohertz. Whereas in multi-cycle, my one clock cycle is basically can be 1 gigahertz, right? A lot faster. So are you with me so far? Basically, this is a rough idea of what I want to get out of this lecture. First of all, how to roughly build a processor. Second of all, how to kind of like, what's the trade-off between a single cycle architecture versus multi-cycle architecture before we do pipelining on Thursday. And don't worry about the yeah, that's it for the class today. I have slides for some reason that are from last semester, so don't worry about this before we leave today thing. Not relevant for you. You're confused about why can multi-cycle architecture be clocked so fast? Okay, that's a great question, right? Multi-cycle architecture basically tell you that I want to clock it in a way that if I have to do a slow instruction, I would spend multiple clock cycle to do it. In the first cycle, I would just make sure I have the address for my program counter, right? Exactly. So there's another private comment where a single cycle architecture, you need to pick the slowest command as the cycle because you need to make sure you can finish everything in one cycle. So that's why you need to pick the slowest one, right? In multi-cycle architecture, you don't care anymore, right? You can clock things as fast as you want, and everything will take multiple cycles. So, and you can even clock faster. You can clock it super fast so that XOR take 10 cycles, add will take 20 cycles, multiply will take 40 cycles, right? As long as you can make sure you can pick the value for the select line in time, you're good. So it doesn't matter anymore what instruction you have to support in terms of figuring out the speed of your clock. You decouple that. As long as you can select at the right time, that's it. That's another great question. So the question is, how does overclocking work in the backend? So so let me ask you this first question. When you see overclocking, what does it do? Boost the speed for the CPU, right? So basically I clock it a lot faster. It kind of means that things that would take one cycle, let's say I have to do an add, right? I have to do an add. My add, let me go back to the diagram, by the way, so that I can clarify this. When I have to forward this data over from here to here, let's say it used to take 1 nanosecond, right? If I overclock from say 3 gigahertz to 6 gigahertz, the clock is twice faster. This time would get cut short to somehow within half of the nanosecond, I need to make sure electron move all the way there, right? The instruction move all the way there. So what does it mean? It means that there's a chance that my electron doesn't get to reach the destination, right? It's not leaking. It's just basically you don't have the value yet, and you move to the next cycle. Right? So it means that your processor would compute wrong thing. The second thing that can happen, blue screen. The second thing that can happen, it heat up because it's too fast, right? So the temperature go up. Another way you can basically cook things. There's another question about, so the instruction has finished executing and storing, and there's still cycle left in the clock in the system, just waiting. Actually, that's a great question. So the question asks, if I say finish my instruction and finish storing, right? And it's not the end of my clock cycle. What do I do? Is that correct? So do I interpret that question correctly? Yeah. So in that case, it's sitting idly doing nothing. So basically, you're correct. We don't do anything. We wait until the next cycle. There's another comment about stronger voltage. So you can overclock by increasing the voltage as well, right? When you increase the voltage, what happened to the electron? Move faster, right? So it moves faster. So in that case, you can overclock as well. Make sure you supply more voltage. What's the downside of more voltage? Yay, barbecue, right? So more heat, component die faster, right? Basically, think of component as a like actual physical thing. If you keep it heat up all the time, it's gonna break faster, right? Is that bad for the environment? So from the power point of view, right? It can. It can. Basically, this is the argument between energy efficiency, which is performance per watt. How much performance do I get per amount of power you are actually basically have to deliver? So should we underclock instead? I think it depends on the performance per watt, because from the user point of view, we would like to have more performance, right? So as long as you're not making it too fast and it burns so much power, you're good. At the end of the day, you're not caring. Let me put it this way, right? Between energy and power, for the environment, which one should you care more? How much energy do you use, or how much power do you use? So back to the question about overclocking. If it overclock too hard, it shouldn't work. And I think I missed a bunch of chat, my bad. Yeah, so if you think about the environment, I think what you care about is the energy aspect, like how much energy do you use? And energy is P equals energy over time, right? Back to basic, like high school physics. Power equals energy over time. So depends on your power that you are supplying your CPU. What is T? Anything that relates to the time is your performance, right? So if T go lower, but P go higher, can I have the same energy output? I mean, possibly, right? Because your energy is P multiplied by T. If I overclock, P go up, power go up, performance go up too. So time goes down. It takes less time to finish my program. Energy is unknown. It can go up or go down, right? I'll give you one example. The way GPU actually work when it render a game, right? Each frame, what it does is it would clock it really fast so that it's finished that frame and it stop running until you need to render the next frame. So it would be a burst of energy and then nothing. Another burst of energy and then nothing, right? And the GPU figure out, okay, that's really energy efficient because you finish quickly and you actually power everything off. Well, not totally off, but relatively low power. On the low power CPU is another inverse of that. You make the input voltage low so that you can clock it not as high, right? To reduce the power. But your program might take a little bit more time, but it consumes less of your battery. It consumes less of your battery so that the battery lasts longer, right? So that's why I said it kind of depends. Any other questions? But we do have a quick. This is interesting. So I hope the lecture is not way too confusing. I'm sorry about using all the time. I thought we have like maybe 20 minutes left. Turned out we have 8 minutes. If anything's too confusing, let's do a question and answer either through the chat. You can open your mic to just basically give your opinion about like things. I'm gonna be here until 4. I have another meeting at 4 with a student, so I have to be here until 4. But if you still have any question left, feel free to either put it on Discord or email. I hope this new and interesting for you, and I'm aware it's also a lot of new material. So if you have questions that you want to ask later, feel free to let me know. I will likely to have more like a open Q&A at the beginning of the next lecture in the first 10 minutes of class while people are still coming in, because I figure that's the time I'm waiting for everyone anyway. So let's do that. All right. And that's it for the lecture today. So I'm gonna open the floor up to the Q&A. If you have any questions, let me know. All right. I'm gonna do it here in WebEx. I don't think there's a need to migrate over to Discord because it's otherwise it's gonna take 5 more minutes. So I'm gonna stop the recording, and I'll make sure I post